Have you ever just stopped and wondered how a photo or a song or even this very explainer gets squeezed into a machine that really only understands two things, on and off? I mean, it seems impossible, right? But today, that's exactly what we're going to do. We're cracking the code, and we're going to translate our rich, kind of chaotic world into the simple, elegant language of computers.
And this, right here, this is the central mystery we're tackling. How on earth do you build an entire digital universe from just two options? It feels like it shouldn't work, but the secret, well, it isn't magic. It's all about structure. It all comes down to a really clever system of organization that turns these simple little switches into incredibly complex ideas.
So here's our game plan for cracking this code. First, we'll get into the fundamental language gap between us and machines. Then we'll check out the shorthands we invented to bridge that gap. We'll get our hands dirty with the art of translation, including a super clever trick for handling negative numbers. And finally, we'll see how it all comes together to bring everything from text to emojis right to your screen.
Okay, let's start with the absolute basics, the fundamental difference. It really all begins with how we count. We humans think in a way that just feels natural to us. But computers? Well, they were built from the ground up to think in a completely different and, honestly, a radically simpler way.
And here's the why behind it all. For us, it's pretty obvious. We use a base 10 system with 10 digits, most likely because, well, we have 10 fingers. It's biological. But computers are built from millions, even billions of microscopic switches called transistors. And each one of those switches has only two possible states, on or off. That's it. This physical limitation defines their entire language, a 1 for on and a 0 for off.
So this single on or off state is the absolute atom of all digital information. We call it the bit. It is the smallest possible piece of data you can have. But you know, one bit isn't very useful by itself. So we group 8 of them together to form what's called a byte. And a byte is way more powerful. It's actually enough information to represent a single character, like the letter A.
Now, computers only speak binary. That's their native tongue. But trying to read these long strings of ones and zeros would drive any person completely nuts. So that's why programmers developed some helpful shorthand. You can almost think of them as digital dialects, just to make the language a little more manageable for us.
So here are the main systems we're talking about. We've got decimal and binary down, but then look at octal, which uses 8 digits, and hexadecimal, which needs 16. And this creates a kind of funny problem, right? We literally run out of number symbols after 9, so what's the solution? Just start using letters. So in hex, A is 10, B is 11, and you go all the way up to F, which stands for 15.
And let's be super clear about this. Octal and hexadecimal are not for the computer. It doesn't need them. It doesn't care. They are for us. They're just a compact, convenient shorthand that lets us humans read and write these incredibly long strings of binary without our eyes glazing over.
So we know the different dialects now, but how do we actually translate between them? This is where we get into the practical art of conversion.
All right, first up, let's tackle the most common translation there is, taking a number we understand, like, say, 25, and turning it into a string of ones and zeros that a computer can actually work with. You know, the method for this is actually beautifully simple. You just keep dividing your number by 2, and each time you just jot down the remainder. Now think about it. Since you're dividing by 2, that remainder is always going to be either a 0 or a 1. So you keep doing this until you hit 0, then you just read that list of remainders you wrote down from the bottom up, and boom, that's your binary number.
Okay, but what about going the other way? How do we take a string of ones and zeros from the machine and translate it back into a number that makes sense to us? This one's called the place value method, and it's just like our own decimal system. You know how we have a ones column, a tens column, hundreds column? Well, binary works the exact same way, but the columns are all powers of 2. So you have the ones place, the twos place, the fours place, the eights, and so on. To get the total, you just add up the value of every single column that has a 1 in it. Simple as that.
All right, we've totally handled positive whole numbers, but what about negative ones? This is where things get really clever.
No, seriously, think about it for a second. We just pop a little minus sign in front of a number. But a computer doesn't have symbols. It's only got ones and zeros. So how does it do it? It has to actually use one of its bits, following a very specific rule, to signal that a number is negative.
Well, the first few attempts at this had a huge critical flaw. Systems like sign and magnitude and ones complement ended up creating two different binary patterns for the number 0, a positive 0 and a negative 0.
And for calculations, that's an absolute disaster. It just breaks basic math and wastes a ton of processing power.
So clearly, we needed a better way, and we found it in a system called 2's complement. This is the elegant standard that every single modern computer uses. It completely solved that 2 zeros problem, and as a really nice bonus, it made the computer's internal math way, way simpler.
And the process itself is just beautifully simple. You start with your positive binary number. Step 1, you flip every single bit. All the zeros become ones, and all the ones become zeros. Step 2, you just add 1 to that result. That's it. You now have the perfect negative representation of that number, and it's ready for any calculation the computer needs to do.
So we've cracked numbers. But what about everything else we see on screen? Well, as it turns out, the exact same principles apply. Every letter, every symbol, every emoji you've ever used is also, at its very core, just a number.
Early on, we had a system called ASCII, which was fine, if you only spoke English. It was basically a simple chart that assigned a unique number to each English letter and symbol. But for a global internet, it was totally inadequate. And that's why we now have Unicode. It's this massive universal standard that assigns a unique number to literally every character in every language on Earth. And yes, that includes all those emojis we love.
So when you really get down to it, it all comes down to this. When you type the letter B or you send a thumbs up emoji, your computer doesn't see a letter or a picture. It just sees a unique number from that big Unicode chart, which it then stores as a string of ones and zeros. Underneath it all, absolutely everything is just numbers.
But with billions of these bits flying around all the time, how do we make sure there aren't any errors? Well, one simple trick is called a parity bit. It's an extra bit that gets tacked onto a byte purely for proofreading. Its job is to make sure the total number of ones is always even or always odd. That way, the computer can instantly spot if a bit has flipped by mistake. It's a simple but really effective little safety net.
So there we have it. We've cracked the code of today's computers, this really elegant system built on the simple foundation of on and off. But as new technologies like quantum computing start to emerge, where a bit can actually be both on and off at the same time, it raises a really fascinating question. Will this language of ones and zeros still be enough? What will the code of tomorrow even look like?